It really is striking how much the conversation around healthcare has shifted towards data. It's not just about keeping charts anymore, is it? It feels like the engine driving things.
Absolutely. It's driving improvements in patient care, operational efficiency. I mean,
Hmm.
think about the sheer volume of information generated every single day.
Yeah, exactly. And making sense of it all, that's the real challenge and the opportunity.
Precisely.
Which brings us neatly to what we're diving into today. One of you actually reached out wanting us to really get under the hood of healthcare data.
Right. How it's collected, the pitfalls, the practical steps.
Yeah, what insights can we actually pull from it? So we've gathered a whole range of information looking at, well, everything from the initial gathering to analysis, ethics, even what's coming next.
And our goal is really to distill the essential stuff, cut through some of the complexity, and give you a clear, usable understanding.
So we'll kick things off looking at how data is actually collected, that coordinated process,
Mhm.
then validating it, making sure it's reliable.
Crucial step. Then we'll navigate the legal and ethical side, which is, hugely important.
Mm.
Then we'll look at the different types of data, how we measure them, get into some analysis methods.
Statistical tools, quality improvement tools.
Exactly. Visualization, comparative analysis,
Hmm.
and then a little peek into the future.
Okay, great. Let's unpack this then. Starting right at the beginning, coordinating the actual data collection. It's not just grabbing numbers randomly, is it?
Not at all.
Okay.
No, it's quite structured. The very first thing, and this is fundamental, is defining your purpose. Why are you collecting this data?
Okay.
And who are you focusing on? Your population of interest.
So, like, give me an example.
Okay, let's say a hospital wants to reduce surgical site infections, SSIs. They wouldn't just look at all surgeries vaguely.
Right. Too broad.
Exactly. They'd likely narrow it down, maybe specific procedures like hip replacements, perhaps focusing on patients with diabetes, over a specific time frame.
Ah, so really specific. SSIs in diabetic patients undergoing hip replacements between January and June, something like that.
Precisely. That clarity up front makes everything else much more effective.
Yeah.
You need that focus.
Makes sense. So once you have that focus, how do you decide who to collect data from? Do you need every single patient who fits that description?
Not always. That's where sampling comes in. You might use a simple random sample if you just need a general overview.
Okay.
But if you need to ensure different groups are represented, maybe different age brackets or severity levels, you might use stratified sampling.
So you make sure you get, say, enough older patients and enough younger patients.
Exactly. Or maybe cluster sampling if your data naturally groups like different hospital wards or clinics.
Hmm.
Importantly, you need software to help design these samples effectively. Things like R or Python are powerful tools for this.
And you need enough people in the sample, right?
Yeah.
Not just 5 patients.
Absolutely. Sample size is critical for getting meaningful results. There are tools like GPower that help calculate how large your sample needs to be.
Got it. So we know the why, we know the who. Now, what about the what's? What specific information do we collect?
That's about selecting the right measures and metrics. You need to clearly define your numerator, what you're counting, like the number of infections,
Right.
and your denominator, the total group you're measuring from, like the total number of those specific hip replacements.
Okay. Numerator over denominator gives you the rate.
Correct. And using standardized metrics, say from CMS or the National Quality Forum and QF, is really valuable. It lets you compare your results to others.
Ah, so you can benchmark.
Yes. And there's a growing focus on patient-reported outcome measures, PROMs.
PROMs, what are those exactly?
They capture the patient's own perspective on their health. Things like pain levels, quality of life, functional status, stuff you don't always get from just clinical tests.
Ah, okay. That's subjective experience. That adds a really important layer.
It really does.
So we know what we want to measure. How do we physically get that information? What tools are we using?
Well, it varies. Could be traditional paper forms, though less common now.
Yeah.
Often it's built-in modules within the electronic health record, the EHR,
Right.
or specific data collection apps on tablets or phones. The key is choosing a tool that fits the data type and, crucially, how you plan to analyze it later.
And you have to test these tools first, I imagine.
Oh, absolutely. Pilot testing is vital. Make sure the forms or apps are clear, easy to use, and actually capture the data accurately before you roll them out fully.
Makes sense. Any newer tech-making waves here?
Definitely. Cloud-based platforms like RDCap are becoming quite standard, especially in research. And wearable devices are increasingly important.
Like fitness trackers, smartwatches.
Exactly. They can provide continuous real-time data on activity, heart rate, even glucose levels for diabetics.
Interesting. But hang on, if you have multiple people entering data, maybe nurses on different shifts using an EHR module, how do you make sure they're all doing it the same way, consistently?
That's a huge point. It's called inter-rater reliability. And the answer is training. Thorough, standardized training for everyone involved.
So clear rules and protocols.
Yes, standardized protocols are essential, sometimes even simulation exercises, especially for complex EHR tasks.
Right. Practice makes perfect, or at least consistent.
And because these systems and standards like the FHIR standard for data exchange are always evolving, that training can't be a one-off. It needs to be ongoing.
Continuous training. That makes sense. Things change so fast. Okay, so we've got the data collection planned out. What about thinking ahead to actually using the data?
You absolutely have to plan for analysis right from the start. It shapes how you collect the data.
How so?
Well, you need to think, what statistical tools might I use?
Mhm.
Regression analysis to find relationships, maybe natural language processing, NLP if I have lots of text nodes,
Okay.
or simpler QI tools like control charts to track things over time and how will I visualize it? Run charts, Pareto charts, maybe an interactive dashboard using something like Tableau or Power BI.
So the end use dictates the beginning.
To a large extent, yes. You need to ensure the data is collected in the right format for your intended analysis and visualization. Like if you're doing time series analysis, you absolutely need accurate timestamps on everything.
Right. Planning the analysis and visualization early helps focus the collection. It's all linked. You mentioned AI and IoT earlier. How are they really changing the game in data collection?
They're having a massive impact. AI, especially NLP, lets us unlock insights from unstructured data doctors' notes, reports that used to be really hard to analyze systematically.
So it can read and understand text.
Essentially, yes. And IoT devices, those wearables and smart monitors, give us that constant stream of real-time patient data. It allows for much more proactive monitoring and intervention.
Are there examples of this working well?
Yeah, definitely. There was a 2023 study in the Lancet Digital Health showing AI significantly reducing documentation errors. And a JAMA article from this year, 2024, highlighted how IoT devices helped cut hospital readmissions for heart failure patients.
Wow, that's powerful stuff. Real impact.
It is, but it also brings challenges, of course.
Like what? I can imagine systems not talking to each other.
Exactly. Data silos are a huge problem. Different departments, different systems holding data captive. The solution really lies in improving EHR interoperability, pushing for standards like HL7 FHIR to make data sharing smoother.
Okay, interoperability. What else?
Staff turnover can be disruptive, which again highlights the need for really good standardized training and maybe knowledge repositories so information isn't lost when people leave.
Right.
And overarching everything is patient privacy. We need robust de-identification techniques and strict adherence to rules like HIPAA, especially with all this sensitive data flowing around.
The identification and HIPAA compliance.
Got it. Okay, so let's say we've collected our data carefully. How do we know it's any good? How do we validate it?
Data validation. It's absolutely critical because if your data is inaccurate or incomplete, any analysis you do on it is basically useless.
Right, the old garbage in, garbage out problem.
Exactly that. So validation is about ensuring accuracy and completeness. What are the main steps involved in validating data?
First is organization. Getting your data into a structured format, maybe Excel, maybe a database like Access, or statistical software like SAS or SPSS. For many QI projects, a simple spreadsheet is often sufficient initially.
Just getting all laid out clearly.
Yeah, like keeping the raw data on a single worksheet, a clear column headers for everything. Simple, but important.
Okay, organized. What's next? Hunting for errors.
That's the scrubbing phase.
Yeah.
You're looking for obvious mistakes, negative values where they can't exist, weird date formats, blank cells that should have data.
Checking for consistency, too.
Yes, vital. Are terms used consistently? Is male sometimes entered as M? Is everything case sensitive when it shouldn't be?
Yeah.
Tools like Excel actually have built-in data validation rules you can set up.
So you can set rules before data entry to prevent some errors.
Precisely. You can restrict entries to only numbers, specific date formats, or drop down lists of approved terms. It helps catch errors at the source.
Clever. What else is involved in validation?
Cross-validation is important. This often involves having an independent person recollect a small sample of the data and comparing it to the main data set.
Like a spot check by someone else.
Exactly. If you find discrepancies, you need to dig into why. Was it a data entry error? Misinterpretation of the collection protocol? Automated tools within EHRs are also starting to help with this.
Okay, independent review. And documenting all this cleaning and checking seems crucial, but maybe easy to skip?
Can't skip it. Documentation is critical for transparency and reproducibility.
Hmm.
You need to keep your original raw data safe and untouched.
Right.
Then clearly label any cleaned or modified datasets. And you absolutely must document the entire validation process, what you checked, what errors you found, how you fixed them. This could be a separate log file or even notes within the data file itself.
So anyone looking later can see exactly what happened to the data. Makes total sense. You mentioned Excel quite a bit. Any specific best practices for using it in this context?
Yeah, a few practical things help. Keep raw data on one sheet. If you have numerators and denominators, put them in separate columns, then calculate the rate in a third column.
Don't just type the rate.
No, calculate it so it's transparent and updates if the source data changes. For missing data, leave the cell blank, don't put a 0, as that could be misinterpreted as an actual value.
Okay. Blank for missing.
Keep code sheets or notes on separate tabs to keep the main data tidy. Limit who can edit the data. Enforce clear entry rules. And the simple one, enter data exactly as collected. No rounding unless that's part of the defined process.
And Excel has features to help spot issues.
Yes, conditional formatting is great for highlighting potential outliers or values that fall outside expected ranges based on rules you set.
Those are really useful practical tips. What about more advanced validation techniques? You mentioned AI earlier.
Right. We're seeing more use of machine learning for things like anomaly detection.
Mhm.
Algorithms can scan huge data sets and flag unusual patterns or outliers much faster than a human could. There are also data profiling tools, like Talent or Informatica, that analyze the structure and quality of your data automatically. And blockchain is emerging as a potential way to create tamper-proof data logs, really boosting integrity, though it's still early days for widespread use in healthcare.
Blockchain for data integrity.
Yeah.
Fascinating. What are some really common errors people find in healthcare data? And how do we stop them?
Oh, the usual suspects. Simple typos, spelling mistakes. Inconsistent date formats are a big one. MMD-DYY versus DDMM-YYY can mess up time-based analyses.
Yeah, I can see that.
Values that are clearly out of range, a temperature of 200 degrees Fahrenheit, for example. And of course, missing data.
And mitigation.
Spell check helps with typos. Enforcing a single date format is crucial. Setting those validation rules in your data entry tool catches out-of-range values. Missing data is trickier. Sometimes you can use statistical techniques like imputation to estimate values if only a few are missing, but often you just have to exclude records with too much missing information from certain analyses. Clear protocols and checks up front are the best prevention.
Okay, so collect carefully, validate rigorously. Now let's shift to understanding the data itself. What are the basic types we deal with in healthcare?
Fundamentally, you've got two main buckets: categorical data and continuous data.
Categorical is categories.
Yep. Groups or labels. You have nominal categories where there's no inherent order like blood type, A, B, A, B, O, or insurance provider.
Right.
Then you have ordinal categories where there is a meaningful order, but the gaps between the categories aren't necessarily equal. Think of a pain scale from 1 to 10 or staging for cancer. A 4 is worse than a 3, but the difference between 3 and 4 might not be the same as between 7 and 8.
Got it. Nominal, no order. Ordinal has order. How do we analyze these?
Often with frequency counts, percentages, maybe chi-square tests to look for associations, or visualizing with bar charts or Pareto charts.
Okay. And the other bucket was continuous data.
Right. This is data that can theoretically take any value within a range and is measured on a scale. Things like temperature, weight, height, blood pressure.
Numbers you can measure precisely.
Exactly. Within continuous, you have interval data, where the intervals between values are equal, but there's no true zero. Temperature in Celsius or Fahrenheit is a classic example. 0 degrees doesn't mean no temperature. And then you have ratio data, which has equal intervals and a true 0 point. Weight, height, pulse rate 0 means the absence of that thing. This distinction matters for certain statistical operations.
And how do we analyze continuous data, typically?
Using methods like calculating means and standard deviations, B-tests, regression analysis, and, it's increasingly common, especially in predictive modeling, to use a mix of both categorical and continuous data.
Right. Real-world problems rarely fit neat boxes. So once we have this data, how do we find the middle or the typical value?
That's where measures of central tendency come in. The most familiar is the mean, the simple average.
Oh, yeah.
Sum up all the values and divide by the count.
Good old average.
Yep. Great for continuous data that's fairly symmetrical without extreme values, like average length of stay. But the mean is very sensitive to outliers. A few very high or low values could pull it way off.
Ah, so one patient staying for 100 days could really skew the average length of stay.
Exactly. In those situations, the median is often better. That's the middle value when you line all the data points up in order. Half the values are above it, half are below. It's not affected by those extreme outliers.
Okay, median for skewed data. What else?
There's also the mode. That's simply the value that appears most frequently in the data set. It's useful for categorical data, obviously, but also for continuous data if you have distinct peaks in your distribution.
Like the most common diagnosis code?
Precisely. Statistical software makes finding these easy, and there are even variations like the trimmed mean, where you remove a certain percentage of the highest and lowest values before calculating the average to reduce the impact of outliers.
Interesting. What if some data points are just more important than others?
Then you might use a weighted mean. You assign a weight or importance factor to each data point before calculating the average.
Like how?
For example, hospital reimbursement might be based on several quality metrics, but perhaps patient satisfaction scores are given double the weight compared to another metric when calculating the overall score and payment.
Got it. So you can emphasize certain factors. Okay, that's the middle. What about how spread out the data is? The variability.
That's where measures of dispersion come in. The simplest is the range, just the difference between the highest and lowest value.
Easy, but probably affected by outliers too.
Very much so. A single extreme value defines the whole range. So frequency distribution is more informative. It shows how often each value or range of values occurs. You can see the whole spread.
Like in a histogram.
Exactly. A histogram is a visual representation of a frequency distribution. But the most common and powerful measure of dispersion is the standard deviation, often abbreviated as SD.
Standard deviation. Heard of it, but what does it really tell us?
It measures the average amount that each data point deviates or differs from the mean of the data set.
So average distance from the average?
Kind of, yeah. A small standard deviation means most data points are clustered tightly around the mean low variability. A large standard deviation means the data points are spread out over a wider range, high variability.
So if you were looking at waiting times, a small SD would mean most patients wait a similar amount of time.
Exactly. A large SD would mean some wait a short time, some wait a very long time. It tells you about the consistency of the process.
Okay, that makes sense. And we often hear about the normal distribution or the bell curve. What's that about?
The normal distribution is a specific, symmetrical bell-shaped curve where the mean, median, and mode are all the same point right in the center. A lot of natural phenomena approximate this shape.
Like people's heights.
Often, yes. In a perfect normal distribution, predictable percentages of the data fall within certain standard deviations from the mean.
But not all healthcare data looks like a perfect bell curve, right?
Oh, definitely not. Data is often skewed. You can have positive skew, where the tail stretches out to the right. This means you have a bunch of lower values and then a few unusually high values pulling the mean up.
Like our length of stay example earlier.
Exactly. Or you can have negative skew, where the tail goes to the left, lots of higher values, and a few unusually low ones pulling the mean down.
And how does skew affect those central tendency measures?
In skewed data, the mean gets pulled towards the long tail. The median is less affected, so it often gives a better representation of the typical value in skewed distributions. The mode stays at the peak. We can actually calculate metrics like skewness and kurtosis to quantify how much a distribution deviates from normal.
So understanding the shape, the distribution is really key before you start analyzing.
Absolutely. It guides your choice of statistics and how you interpret the results.
Okay, that's a great foundation on data types and basic measures. Now let's get into some specific statistical tests often used in healthcare analysis. What's the deal with the chi-square test?
Right, the chi-square test. It's primarily used when you're working with categorical data. Its main job is to help you figure out if there's a statistically significant association between two or more categorical variables.
Association. Like, are two things related?
Exactly. For example, are patients in Ward A more likely to get an infection than patients in Ward B? Or is there a relationship between smoking status, smoker, non-smoker, and developing a certain respiratory condition? Yes is now. Chi-square helps answer that.
How does it work, in simple terms?
It compares the frequencies you actually observed in your data categories.
Okay, real numbers.
With the frequencies you would expect to see if there was absolutely no relationship between the variables, basically what you'd expect by chance.
Observed versus expected.
Right. If the difference between observed and expected is large enough, the test gives you a chi-square statistic and a p-value. A small p-value, typically less than 0.05, suggests the association you observed is unlikely to be just random chance.
So it suggests a real relationship.
It suggests the variables aren't independent, yes. Software like R makes the calculation straightforward with functions like chysq.test.
Got it. Chi-square for categorical relationships. What about comparing averages between groups? Like, did a new drug lower blood pressure more than a placebo?
That's where the t-test comes in handy. The t-test is used to compare the means of a continuous variable between two groups.
Only two groups.
For the basic t-test, yes. There are variations for more groups, like ANOVA, but the t-test looks at two. There's the independent t-test, used when the two groups are separate, like your drug versus placebo example, or comparing average wait times in Clinic A versus Clinic B.
Okay, independent groups.
Then there's the paired t-test. You use that when you have two measurements from the same group, often before and after an intervention, like measuring patients' pain scores before physical therapy and then again afterward.
Comparing the same person or thing at 2 points in time.
Exactly. Like chi-square, the t-test calculates a statistic, the t-statistic, and a p-value. Again, a small p-value suggests the difference in means between the two groups, or time points, is statistically significant.
And software helps here too.
Oh yeah, SPSS, Python SciPy library, R, they all do t-tests easily.
Okay, t-tests for comparing two means. We also hear a lot about regression analysis. What's that all about?
Regression is really powerful. It's about examining the relationship between variables, and often using that relationship to make predictions.
How does one variable affect another?
Exactly. You have a dependent variable, the outcome you're interested in,
Yeah.
and one or more independent variables, the factors you think might influence that outcome.
Give me an example.
Okay, maybe you want to predict hospital costs, dependent variable. You might look at patient age and length of stay, independent variables, using multiple linear regression.
Yeah.
It tries to find the best straight line relationship.
So as age goes up, costs go up, maybe.
It can quantify that relationship. Or if your outcome is binary yes-no, like hospital readmission yes-no, you'd use logistic regression. Regression also often gives you a correlation coefficient, RRA, which tells you the strength and direction of a linear association between two variables.
And this ties into machine learning too.
Absolutely. Many machine learning prediction models are essentially advanced forms of regression, using frameworks like TensorFlow or scikit-learn to handle much more complex relationships and larger data sets.
So these statistical tests help us move beyond just describing data to really understanding relationships and making predictions. That's powerful for decision making.
Incredibly valuable, yes. It provides the evidence base for improving care.
Okay, now let's connect this analysis back to practical improvements. Healthcare is constantly trying to get better. What tools help analyze data specifically for quality improvement or QI?
Right, there's a whole toolkit for QI. These tools are often very visual and help teams understand processes, identify problems, and track changes over time.
What are some common ones?
You see run charts and control charts a lot for tracking data over time. Histograms for looking at distributions. Pareto charts for prioritizing issues. Cause and effect diagrams or fishbone diagrams for brainstorming root causes. And flow charts for mapping out processes.
And these are integrated into systems now.
Increasingly, yes. Many EHRs, like Epic, have built-in QI dashboards that incorporate some of these tools, making them more accessible for frontline teams.
Let's look at a couple. What's a run chart tell you?
A run chart is basically a line graph plotting data over time. Time on the x-axis, your measure on the y-axis. Usually plot a center line too, often the median.
What are you looking for on it?
You're looking for non-random patterns. Things like a shift, 7 or more consecutive points all above or all below the median. Or a trend, 5 or 6 points all going up or all going down. Or too few or too many runs, which are groups of points on one side of the median. These signal that something might have changed in the process you're measuring.
So if a clinic tracks weekly wait times and sees 7 straight weeks above the median after changing their schedule, that's a signal.
Exactly. It suggests the change might have had an effect, possibly unintended.
Okay. How is a control chart different? It also tracks data over time, right?
It does, but it adds statistical control limits, usually an upper control limit, UCL, and a lower control limit, LCL. These are typically set at plus and minus 3 standard deviations from the mean.
3 standard deviations. Why that number?
It's based on statistical theory. In a stable process, points falling outside those limits are very unlikely to happen just by random chance.
So points outside the limits are a stronger signal than just a run on a run chart.
Generally, yes. Control charts help you distinguish between common cause variation, the normal expected fluctuations, a stable process, and special cause variation signals that something specific and assignable has changed or gone wrong. A point outside the limits is a sign of special cause variation.
So, if a hospital tracks patient complaints per month on a control chart, and 1 month spikes above the UCL, they investigate that specific month.
Precisely. It tells them something unusual likely happened that month, warranting a closer look.
Got it. Now, Pareto charts, you mentioned prioritization. How do they work?
Pareto charts are based on the 80-20 rule, the idea that often about 80% of the problems come from about 20% of the causes.
The vital few.
Exactly. A Pareto chart is a bar chart where you plot the different types or causes of a problem, ordered from the most frequent on the left to the least frequent on the right. You also usually add a line showing the cumulative percentage.
How does that help prioritize?
It visually highlights the vital few bars on the left that account for the bulk of the problem. So if you're analyzing medication errors, a Pareto chart might quickly show that, say, transcription errors and wrong dosage account for 75% of all errors.
So you focus your efforts on fixing those two things first for the biggest impact.
That's the idea. Maximum impact with focused effort.
Makes sense. What about cause and effect diagrams? The fishbone ones.
Right, the fishbone or Ishikawa diagram. It's a brainstorming tool. You put the problem or effect you're investigating at the head of the fish. Then you draw main bones branching off, representing major categories of potential causes.
Like what categories?
Common ones are people, process equipment, materials, environment, measurement. Then the team brainstorms specific potential causes within each category that could be contributing to the main problem.
So for delayed patient transfers, you might brainstorm staffing issues under people, communication breakdowns under process, lack of wheelchairs under equipment, and so on.
Exactly. It helps organize thinking and ensures you consider different angles to find the true root causes.
And lastly, flowcharts. Just drawing out the steps.
Pretty much, yes. But using standardized symbols to represent actions, decisions, delays, input-outputs. Mapping a process visually like this is incredibly helpful for understanding how it actually works, not just how people think it works.
And that helps find problems.
Oh, definitely. You can spot bottlenecks, redundant steps, points where errors frequently occur, or unnecessary complexity just by looking at the flowchart. Mapping the patient admission process, for instance, can reveal all sorts of inefficiencies.
So these QI tools really provide a practical way to use data to see problems and figure out solutions.
Exactly. They bridge the gap between data analysis and tangible improvement actions.
Okay, we've got good data, analyzed it, maybe used QI tools, but how do we share what we found effectively? That brings us to visualization, right?
Absolutely. You can do the best analysis in the world, but if you can't communicate it clearly, it won't lead to action. Good data visualization tells the story in the data.
So beyond the QI charts, what are common ways to visualize healthcare data for reports or presentations?
Well, you have basic frequency plots like dot plots or histograms, great for showing the shape and spread of a single variable like patient ages or lab results.
Okay.
Bar charts are workhorses for comparing quantities across different categories, infection rates by hospital unit, or procedure counts by surgeon.
Simple and clear.
Pie charts can show proportions of a whole, like the percentage breakdown of different types of insurance payers. But use them cautiously. If you have too many slices, they get hard to read. Bar charts are often better for comparison.
Right. The eye is better at comparing lengths than angles.
Exactly. And then, of course, run charts and control charts are crucial for showing trends and variation over time, as we discussed. Pareto charts for that prioritization piece.
With all these options, what are the key principles for making visualizations effective? Not just pretty, but clear.
Clarity and simplicity are paramount. Avoid chart junk, unnecessary grids, 3D effects, distracting colors. Use clear, concise titles and labels.
Keep it clean.
Yes. Consistency is also key. Use the same colors, scales, and chart types for similar data across your report or dashboard.
So people don't have to relearn how to read each chart.
Right. Interactivity is also increasingly important, especially in dashboards. Allowing users to filter, drill down, or hover for more details makes the visualization much more powerful.
Let people explore the data themselves.
Exactly. And finally, accessibility. Consider colorblind-friendly palettes, use sufficiently large fonts, and provide text alternatives for visually impaired users. Think WCAG guidelines.
Accessibility, that's really important. You mentioned dashboards, tools like Tableau, Power BI. Why are they so popular?
Because they combine multiple visualizations into one interactive view. Users can see different facets of the data side by side and explore relationships dynamically. They can filter by date range, department, patient type, whatever is relevant.
So it speeds up insight.
Significantly.
Yeah,
Instead of static reports, you have a tool for exploration and faster decision-making.
makes a lot of sense. Okay, so we can visualize our own data, but often we need context. How are we doing compared to others or to our past? That's comparative analysis.
Exactly. Comparative analysis puts your data into context, which is essential for understanding performance. There are really four main goals.
4 goals. Okay.
1. Compare your performance over time. Are we getting better or worse? 2. Compare with peers. How do we stack up against similar hospitals or clinics?
Benchmarking.
Yes. 3. Compare with standards. Are we meeting regulatory requirements or accreditation targets? And 4. Compare with best practices. Are we doing what the evidence shows leads to the best outcomes?
So, time, peers, standards, best practices. Where do we get the data for those comparisons, especially the peer data?
There are several resources. CMS Hospital Compare is a big public one for hospital metrics. AHRQ provides quality indicators. And then there are private organizations like Vizient and Premier that run large benchmarking databases where member hospitals submit data and can compare themselves, often in quite granular detail.
And using these helps hospitals improve.
Research shows it does. Seeing how you compare can be a powerful motivator and helps identify areas where you might learn from top performers.
Can we walk through that SSI example again using comparative analysis?
Sure. So the hospital wants to reduce SSIs. First, they track their own SSI rate over time, comparison over time. Then they use Hospital Compare or Vizient to see how their rate compares to similar hospitals, comparison with peers. They check their rate against targets set by, say, the Joint Commission, comparison with standards. Let's say they find their rate is higher than peers and just meeting the minimum standard.
Not great.
Right. So then they research the literature and find evidence for enhanced sterilization protocols, identifying best practices. They implement these protocols.
Okay, adopt the best practice.
Then they continue tracking their SSI rate. Let's say after implementing the new protocols, their rate drops by 12% over the next 6 months, putting them closer to the top performers, recomparing over time and against peers. That shows the impact.
That really ties it all together, using data and comparisons to drive real change. Okay, final stretch looking ahead. What's on the horizon for healthcare data? What are the big trends?
Oh, it's moving fast. AI and machine learning will become even more integrated, driving predictive analytics for disease risk, treatment optimization, operational forecasting.
More prediction?
Yes. The Internet of Things wearables, remote sensors will provide a flood of real-time patient data, enabling truly continuous monitoring and personalized interventions, especially for chronic diseases.
More data streams.
Blockchain still holds promise for secure, patient-controlled data sharing, though adoption hurdles remain. And further out, maybe quantum computing could revolutionize drug discovery and complex systems modeling using vast data sets.
Quantum. Wow. What about the rules and regulations? How will they keep up?
We'll likely see continued pushes for interoperability, like mandates stemming from the 21st Century Cures Act, forcing systems to talk to each other better. Privacy regulations like HIPAA will need to evolve to address challenges from AI, like algorithmic bias and re-identification risks. We might see updates around 2025 focusing on these areas.
So policy trying to catch up with tech.
And ongoing adoption of global standards like ICD-11 for diagnoses and Sentinome CT for clinical terms will be crucial for data sharing across borders.
And ethically, what are the big challenges we need to grapple with?
Equity is huge. Ensuring AI doesn't perpetuate or worsen existing health disparities. We need bias detection and mitigation built in.
Fairness and algorithms.
Yes. Patient empowerment is another, giving patients meaningful access to and control over their own data through portals, APIs, and transparency. Being open about how data is collected, used, and secured is vital for maintaining trust, especially around sensitive issues like data monetization.
So fairness, empowerment, transparency, key ethical pillars.
Absolutely. Organizations like AMIA are working on frameworks to guide this.
Okay, so wrapping this all up, our deep dive today really underscores that systematic data practices aren't just a nice-to-have in healthcare anymore. They're fundamental.
Couldn't agree more. From careful collection and rigorous validation, through insightful analysis using statistics and QI tools, to clear visualization and comparison, it's the bedrock of improvement.
And understanding these concepts, even at a high level, really empowers everyone involved, clinicians, managers, researchers, even patients, to make better, more informed decisions.
Which ultimately leads to what we all want: safer, higher quality, more efficient care.
Exactly. So, to leave you with something to think about, Considering these incredible advances in AI and the sheer explosion of healthcare data, what do you think are the single most significant ethical challenges we, as individuals and organizations, absolutely must get right to ensure this powerful information is used responsibly and truly benefits everyone in the coming years?
Hmm. That's a big question. Lots to consider there.
Definitely something to mull over as we navigate this data-driven future together.